Our first presentation is about campus research and NSF opportunities related to that. We have John Hoinowski and Brian Murphy from Butler. John is a senior network and security engineer. His IT career began over 16 years ago in the U.S. Army. In addition to the military, he has served as an IT resource in mortgage insurance, healthcare, cloud service provider, and higher education industries. John is currently working toward his MBA at Butler and strives to be a bridge between business and IT. He's working with Brian Murphy, who is a professor of physics and astronomy. And I hope I have this correct. 6 years ago, Brian secured funding allowing for Butler's membership in the Southeastern Association for Research in Astronomy. It's the Telescope Consortium, and this particular endeavor is one of the science drivers in Butler's interest in applying for NSF funding this year. So join me in welcoming John and Brian to the stage.
No, that should be good. Can you guys hear me okay? Yep. All right, so I'm a network guy, and they usually stick us in caves, so excuse my lack of presenting ability. Yeah, so for the next hour, we're going to talk about campus research, collaboration, and NSF opportunities. A little over a year ago, iLight and Internet2 approached us and started talking about opportunities that NSF provides and some of the success stories from Wawasee and Earlham. They were very inspiring, so we decided to look at the NSF, and we've been working on it for about a year, waiting for the 2016 information to come out, and it came out 2 weeks ago, so good timing for us. Presenters today will be myself, senior network and security engineer. I started at Butler about a year and a half ago. Very good place to work. I've had the opportunity to meet the next presenter, who's Brian Murphy, professor of physics and astronomy. He's been there for about 23 years. I mean, this guy is part of the groups that talk about whether or not Pluto is a planet. Very exciting. I'm an astronomy nerd myself. You know, I watch Ancient Aliens and how the universe works, you name it. So for the agenda for today is, I'm just going to give a quick intro here. At some point, we're going to bring Brian up in a few minutes. He's got some really good slides that talk in depth about what his research is. And I know a lot of you who may be pursuing the NSF grant solicitation, you might be wondering what you have that would meet the requirements of the National Science Foundation for these grants. So hopefully this will be a good example for you guys to think about how, what research you have that meets the requirements. After that, Brian's going to hand it back to me. Well, he's going to end it first talking about some of the pain points from his perspective. Then he'll hand it back to me, and we'll talk about pain points from an infrastructure perspective, storage, network. After that, we'll talk a little bit about the process we used to make the rubber meet the road. It's one thing to have these, have your research that you've identified, which is pain point one. How do you extract that information? How do you reach out to your faculty and staff to get all that? And then part two is how do you bridge that between some infrastructure requirement and actually make it a reality so that you can submit a grant request. And then we'll have a little bit of time for questions based on our time availability. So a little bit about Brian Murphy. He's an extremely busy guy, for one. He's a member of the Southeastern Association for Research in Astronomy, and these are universities across the country. I know they have some in Chile. I checked the website. I can't remember exactly where more of them are, but there's about 13 of them, I believe. And Brian's going to come up and talk a little more in depth about himself and some of the collaboration he's doing with astronomy, which is very important to emphasize in this grant. So without further ado, Brian Murphy.
Okay, there we are. Thank you, Sarah. There we are, okay. First off, as he told you, I've been here, or at Butler at least, for 23 years. Before that, actually, I was a graduate at Indiana University. So those of you from Indiana University who might work with their astronomy department, and in particular, I worked with Richard Durson, Halden Cohn, if the IU group knows any of them. But they got me into theoretical astrophysics. I thought I'd start out as an observer. Went into theory, and theory is all about, obviously, computational physics. So it involves a lot of supercomputing and things like that. And obviously, what I used back then is equivalent to almost an iPhone as far as power. And the reason I did that, stayed in theory, is because back in the 1980s, we were still making the transition from photographic plates to digital cameras. Astronomers were among the first, astronomers in NASA were the first to use digital cameras. We've been calling them CCDs forever, okay? And they started to come into play in about the mid-1980s. By that time, I'd made my switch to theory. But my first postdoc was in Utrecht in the Netherlands, and my colleagues there said, you know, you can get some time on these big brand new telescopes in the Canary Islands, you and your colleagues from the States, since you're now in Europe. And I said, okay, I'll apply. I had no idea what I was doing. I was a theorist, okay? I knew how to use a computer, but didn't know how to use a big telescope. I didn't even know how to do digital imaging. Luckily, I had some very good people surrounding me from all across the world when we were doing these observations. And that was my first foray into real observing with the largest telescopes at the time in the world. Well, after that, I came back to the States, had a postdoc at Cornell University, then came back, actually by chance, to Indiana here at Butler University. And the interesting thing was, at the time, I read the ad for Butler University, and it said, okay, we're looking for someone who's a theoretical astrophysicist who knows how to operate a telescope and be an observatory director. And I said, well, I do know a lot about telescopes, and I know how to run smaller telescopes, and I am a good theoretical astrophysicist. At least I can, program my way out of a bag or code my way out of a paper bag, all right? So I figured, okay, it looks like they're looking for me. Evidently they were. I was the ideal fit, because they wanted someone who knew a bit about observations, who could get their telescope, which is, at the time, was the largest telescope in the state. IU temporarily had the advantage of us, and now I think they sold off the telescope they had in Morgan Monroe State Forest. We're back to being the largest telescope in the state. It is a 1-meter mirror. And since the time I came here, we've secured several grants. And what happened in 2002, I was reading the Financial Times. Actually, a colleague of mine was, and he happened to post something on his bulletin board outside his office that was listing the alumni in our department who have gone on to get PhDs. And one of the alumni said he had stock options worth $1 billion. And of course, that catches your eye when you're at a university. Because most of us who go into academics, advancement departments don't go after us, okay? Because they know we're in academics, don't make a lot of money. But those who don't go into academics and go into industry usually make a heck of a lot more. This guy did very well. In fact, his company is called Finisar. I don't know if anyone has ever heard of it. It makes most of the fiber optic switches in the world today. And he graduated from Butler in 1974, and now he's a philanthropist. And so we contacted him, and after much going back and forth, he's also an astrophysicist, PhD, and so he talks like an astrophysicist, throwing the ideas at the wall, and I had to sort of steer him back to what I wanted. Eventually, we sort of came to a conclusion and said, well, why don't we try to get into a telescope consortium? That would be great for a school like Butler University, where we don't have a full-fledged giant astronomy department, say like IU, but we can put ourselves in a consortium that makes us a very large astronomy department with access to telescopes. And so that led to him giving us a donation and create an endowment to pay our dues to join the Southeastern Association for Research in Astronomy. And so after we joined this, and it was actually 2008, I believe we joined, the first telescope they had at the time was Kitt Peak. This was funded in 1994. It was actually, those of you at IU, if you're familiar with the telescope they have at Kitt Peak, Arizona, it is a 4-meter telescope. This telescope used to be on the side of that. So to make way for it, they had to move it. And the National Astronomy Organization said, if anyone wants this scope, it's yours, but you have to move it and rebuild yourself a new observatory. Well, 4 universities in the American Southeast here took that over, got a National Science Foundation grant, and built this observatory here with this first telescope that was on Kitt Peak, Arizona. This is the first national telescope ever to exist in this country, built in 1959, I believe. So by national, I mean that anyone could use it if they apply for time. Prior to that, universities had their own telescopes. And we still have this program today where you can apply for time on national telescopes. It's starting to shift back more to private universities again. And that's why this was an important step for us. So at the time, there was only one telescope out at Kitt Peak, Arizona, a 1-meter telescope similar to the size we have at Butler University. But one of the things that enticed us to join was they said, we'll also, with your, let's call it, admission fee, we're going to get another telescope refurbished that belongs to Lowell Observatory in Cerro Tololo, Chile. That would give us full sky coverage of the northern and southern hemisphere. So that led us to getting another observatory in this consortium. That led to 60 nights a year on telescopes. Now you might say, well, that's a lot of travel time. Well, we don't travel to these observatories. We use them fully remote. I can use them from my laptop watching TV, and in fact I have, sometimes with a margarita, sometimes with on my deck. But anyway, now we are up to actually 3 telescopes. We just commissioned the Jacobus Kapteyn telescope. We have become one of the premier consortiums of using small telescopes, taking old telescopes, refurbishing them, putting great cameras on them. And you can see now that we got a pointer here. The universities, and anyone from Ball State here? Okay, how about Valpo? Okay, all right, we've got the whole crew right there. You guys are in our consortium too, and I consider them part of our big astronomy department, okay? So I know most of the people, I almost know every astronomer in this consortium, which is about 50 of us. And we do act like a large astronomy department, exchanging data between each other. And you can see the list is getting longer and longer. We're probably adding 2 more people or 2 more universities to this in the near future. And now there's competition to get in it. And just a quick thing about this consortium, my colleague and I, Shenming Han at Butler University, he's another astronomer there, we were doing a calculation because we were looking at the WIN consortium, which is what IU belongs to. And this is nothing against IU, but they have a very large, very nice telescope, which I've used out at Kitt Peak. We were calculating the cost per photon to observe. That is, they have a larger aperture, it collects more photons for their telescope. We have 3 telescopes of smaller aperture. But if you add the cost per year, ours was 1/4 the cost, okay, per photon coming into the telescope. So in that way, we are one of the most cost-effective consortiums in the world, if not the most cost-effective consortium in the world in collecting light from space. So anyway, the telescopes we have, first of all, the one at Kitt Peak out in Arizona, and we actually send students, we usually go out there once every year or so with students just so they can get the feel for what it is observing on a mountaintop, which they suddenly realize is roughing it. Because at Kitt Peak, Arizona, they have radio telescopes also, which means you cannot have any Wi-Fi, which means they cannot use their phones, which means they're separated from the outside world, and it's fun to see that, okay? To see college-age students, my phone, what? I can't act. I said, no, you actually have to take this cable and plug the computer into the wall. It's called an Ethernet cable, and they're totally amazed that you actually have to do that. But the Cerro Tololo telescope is sitting down here, and this is also the site, near the site where they're going to build what's called the Large Survey Synoptic Telescope, which is going to create, I think it's 10 terabytes of data a night. All right, and that's going to have to somehow get from here up to North America. The same thing happens with our telescopes. We have to get our data, and we get 80 nights a year on these 3 telescopes, but we have to get our data from these 3 telescopes to Butler University. The bottleneck usually is not necessarily Butler University. It's usually getting out of Cerro Tololo here, for instance. The reason is because everyone's putting telescopes all over the world, and remote observing is now the hot topic to do, and even have robotic telescopes that do your observations for you. And everyone tends to push their data through the pipe off the mountaintop at the same time of day, right after sunrise. And there was, I think South Korea put a telescope on there that was pushing through several terabytes all at once, which was slowing everything down. And there was one point, I think I was getting something in the neighborhood of 50 bytes per second download to Butler. And I sent an email to the director, who is an IU grad also, and he said, and I told him, I said, you know, I could actually fly down there with my flash drive, get the data, and come back to Butler from South America, and it's still a faster rate of getting data across, okay? Nothing like an SUV full of flash drives going down the highway, all right? So anyway, so one of the issues we deal with, and by the way, remote observing is wonderful. I mean, it is absolutely wonderful. My students realize that when they actually have to go to the mountaintop, it is literally sort of roughing it. They have to sleep in something that looks like a dormitory, not even as good as, you know, nowadays they live in Hiltons practically, the students do. But they get out there to these 1950s dormitories, they realize, oh, okay, and watch out for scorpions and occasional mountain lion, things like that. But this telescope here, just to tell you, one of the nice things about astronomy, they tend to be in wonderful locations, or observatories, so it is nice to travel to these. And I was actually at this one here last fall. We traveled out there. This is the board of directors. Some of them, not everyone could make it to the dedication of this telescope. We are now hooked in with the Spanish. They are hooked in with our organization. We send students there now. And so this telescope here, it looks a lot smaller, but it's about a 50-foot high building, has several levels, and it's basically an academic building in its own right. And this sits 8,000 feet. This is the Atlantic Ocean down here, 8,000 feet above the Atlantic Ocean. One of the premier sites in the world. And the fact that a small school like Butler, say Valpo, Ball State, we can all get access to these facilities is really remarkable. Now, one of the things that we deal with in choosing our research program, you know, we suddenly remember, I was a theorist, and we were looking for something that was good for Butler. Well, you know, I had by the way, our donor, Frank Levinson, also gave us a highly parallel computer, too, for theoretical computation. So I had that. Now I had this, and I said, okay, what the heck am I going to do? I'm used to using these massive telescopes that can see very dim objects, but you typically only get 3 nights a year on those. Here, though, I suddenly have 80 nights a year on things that I can't see real dim objects, but I can see a lot of medium, let's say, dim objects, okay? And so the issue was I had to find a research program for that. And given the amount of time I had, I figured, okay, the best thing to do is look for something that varies in time. There are a lot of things out there that vary in time, and that tells you what's happening, say, with a star, with an active galaxy, with a quasar, something exploding known as a gamma ray burst. But that was the thing we decided to go after. Now, you just don't point randomly at the sky and say, okay, I'm going to look at that star, because that star might be quite boring, similar to our sun, which only changes by 0.1% in brightness over the full solar cycle. We wanted something more than that, and we wanted more than one star. So one of the things we picked were globular star clusters. And globular star clusters are literally, you know, it tells you a lot. The word globular, it's sort of like globular, but it's a glob of stars is a way to think of it. And when we actually do the imaging, it typically produces, it's fairly paltry, 2 gigabytes of data, but we have to get that across to Butler, and the images are downloaded. The last student who observes for the night, their task is to start the download. So when I come in at, say, in the summertime, usually is when we observe primarily, is when I come in, I said, I want that data sitting there ready to be processed. That is to get rid of all the image defects, things like that, so we can begin analysis. So, this is a typical globular cluster. You tell me what stars vary in there. If I gave you 1,000 images, could you think out of these 20,000 stars, pick out which stars were varying? How they're changing brightness. And that's the problem with this. And that's why we picked this, though. Here's 20,000 stars we have to choose from. But it's not an obvious thing to see which ones are actually varying. So finding the objects is very difficult. In the old days, I think, how the heck did they do this without digital imaging? Think of having a photographic plate, literally a film emulsion on a plate. You slide at the back of the telescope, only 5% efficiency compared to 95% collecting light efficiency with these. And then one photographic plate, okay, that might be 20 minutes, grab another one, put it in there, put another one, slide another one. Then you, oh, by the way, you have to develop things. I did that in graduate school. That was the last time I said I'm doing observational astronomy, okay? Because I had to develop a photographic plate. And so this, I said, I contacted my old PhD advisor. He's not old, but PhD advisor at IU. And I said, you know, we both worked on globular clusters, but more the theory of what goes on. How do stars move around? How do they collide with each other in these dense stellar conditions? And we contacted one of our colleagues in San Francisco State University. And she told us, she said, well, there's this program. Unfortunately, it was called ISIS, okay? ISIS, okay? I'm going to use the word difference image analysis, okay? Because I'm sure I have an FBI file a mile long from all the emails I have with ISIS in them. But anyway, so the thing was, what ISIS does, it is literally difference image analysis, okay? Imagine the following. If we take two images taken at different times, okay? There we are. At different times. Here's one image. Say here's another one, maybe an hour later. And we subtract the two. If everything's equal on that, that is the background, the sky hasn't changed, the stars are the same. If one is varying, what happens if it's a digital image? You should see a negative or positive instead of a 0 in that subtraction, because you're subtracting all the pixels across the image. This assumes they're aligned, by the way, which they typically aren't, because the telescope can shift a bit in between images. Also, you can have other effects. Well, if you do this naively, subtracting two images, what you find is you get, yeah, you have stars being subtracted. You can't see all of them there as the light shining down, but you can see, zooming into one, you get these donuts. The reason you get donuts is, the fact is, in between just that 2 minutes between those two images, the atmosphere changes. I'm sure we all know Twinkle, Twinkle, Little Star. Well, astronomers hate that, not the song, but they hate the twinkling. That is the biggest problem with astronomy. The atmosphere screws things up for us. We have hot pockets of air rising, cool pockets of air sinking. And so what the issue is trying to correct for that. And so what we do is we create a, well, this shows some of the shimmering. These might be 1 second apart, images of the moon. And what happens, that causes stars to bloat up, to shrink down to what we call really good seen and poor seen. So this is what we, if you look actually on the, digitally at the image, per pixel, you'll see a star rise and have what we call a point spread function across the image. And good seen, this is a lot sharper and goes a lot higher. Most astronomers want the best seen they could probably possibly find. This is one reason the Hubble Space Telescope went up into space, to avoid this seeing issue. So they get pinpoint images. Well, we can't put these telescopes up into space because it increases the cost of the telescope by $1,000. Or not 1,000, 1,000 times, okay? $1,000, yeah, I'll go for that, okay? But anyway, so what we do is we take our best, say, 15, 20 images out of our pool of 2,000 images and create a nice reference image. So this is a combination of our best images. And this has been corrected for all the defects in the image. And by the way, if anyone knows anything about digital imaging here, this is just an overexposed star, which in your standard iPhone camera or Android, they have software to correct for things by putting, I forget, they're almost like canals between the pixels. And this here, obviously, we have bad columns. Your phones have those bad columns too. The software just interpolates and averages and does a median across them, so you don't see them. We want to see those where they're at, so we can know, so we know where. We don't want the software doing things that we aren't sure it's what exactly it's doing. So imagine here, we're trying to find out which stars are variable. So if we use this reference image now, which is our best images we have, and then say, here's an image taken at a certain time. Let's see if any of the stars have changed in that time. What we do then is take this reference image and convolve it to that image. That is, it looks at the point spread function in the image that we're going to look at, changes the stars so they're the same shape, same smeared out by the atmosphere, so to speak, and then do the subtraction. And then it can look at all 2,000 images and go through this. So you start to see it's also a computational problem too. Also, it has to align all the images, so there's pattern recognition. Luckily, stars are easier to recognize than human faces, and the reason is that stars have patterns. So it looks for a series of triangles and combinations and easily can align these images. By easily, I mean in about 30 minutes, it can do 1,000 images or so. But then it goes through and subtracts the images after it does the deconvolution, which is still time-consuming. And then it sends you what's called a residual image. Where does it find all the variance in the image occurring? And this is the variance in that image. Now there's those overexposed stars right there. We ignore those because they have the weird shape to them. But notice all these dots here are stars that have high variance. That means they are varying. Everything else is pretty much black in the background here. Now I've circled one of the stars here to show you this. I'm going to change the reference. Here's the reference image, but I've scaled to black and white for you. Notice that star right there. So let's go back and forth. And you can see the stars, whoops, wrong way, that are varying here. And those stars are very important because they are somewhat in the death throes of their life. They're almost like a beating drum. They're in this unstable phase. But the fact that they're beating like a drum, and just like when you listen to a drum, the sound you hear, the frequencies it's vibrating at, tells you a heck of a lot about that star. Not just the surface, but it's almost like stellar seismology, where you're inspecting the interior of the star itself. So first off, you can see some of the problems we deal with. One, it's getting the data downloaded to us. Okay, that's not necessarily on our end. It's typically the observatories which are fighting all this problem because astronomy is very, very data heavy. In fact, one of the radio telescopes they're building is going to be downloading exabytes per hour, 10 to the 18 bytes per hour. And they don't know how they're going to take care of that. They're going to have to archive, compress, who knows what. I'm sure a lot of the people who are in this room and your colleagues are people who are working on that. Thank God for you people, because I can't survive without the people in this room. But anyway, imagine what we go through here if we take a whole series of images, okay, and we follow, let's say, a single star. We'll watch it vary and stuff, and let's say this is one of the stars that we're varying. Now, what if I draw a line here? Imagine I have 1,500 of these images now, just for a single cluster, for a single season. And I follow a line for every single one of these stars, 20,000 stars. That's a heck of a lot of data right there in itself. Now, each image, these are relatively small images. The raw images are 8 megabytes. But when we process them and do a lot of division, they're 16-bit images to begin, or 16-bit camera to begin with, so that means there's 16 bits per pixel, roughly 2 million pixels, 2048 by 2048, 4 billion pixels, excuse me. I had to do my math there. But the thing is, when we process it, it goes from 16-bit, we add another factor of 2, it goes to, or 8-bit to 16-bit, and then when we analyze it, it pushes up to 32 bits. Now remember I told you you also have to align the images? Well, that adds another 32-bit image that you have to take care of. Then when you convolve the image to match the reference, that prototype gives you another 32 megabyte for that single image. You start multiplying all that times 1,500 for a single cluster over a single season, and you see we have a big data problem. And we start piling up data. Now, the thing is, 200 gigabytes doesn't sound that much, but the problem is you have to multiply this by 5 to 10 just for a single season if you use my colleagues. And that's just for the telescopes I use, which is one of the telescopes in the SARA consortium. So it is an issue. Now the thing is, you might say, okay, you're done with the data, you can get rid of it. No. The reason is when we look at stars, notice this is a 14-month time span here. And this shows what one of those stars is doing. Each night we observe it. You can see it rising and falling. And you might say, why didn't you observe it here? Well, the sun was in the way, okay? And that is an issue. It's the biggest source of light pollution in the sky. And so it came back into view here, and we observed it for another few months while it was easily visible high in the sky from the southern hemisphere. And from this, you might say, well, what does this tell you? Well, if you look, let's, for instance, add a single night here. And so this is now, we've already gone through this ISIS, or difference image analysis. Say, here's all the stars we can see right now that are varying over this 14-month time period. If we look at this single night, you can see here's a star on this very nice up and down curve here. We keep going with that. If we combine all the nights together, what we call phase the data, have a computer do an analysis of this to see what's the period of this variable, how is it varying. Now you can see all the different nights here, and this varying quite nicely. By the way, this star here is 10 million times fainter than what your eye can see when you look in the night sky. And the data is accurate to about 1%, that is variance in the air. So it's amazing what you can do. And this telescope that we're using down there has only 1/2 the area of our Butler telescope, if that. All right, so it's really impressive that we can get this. With difference image analysis is amazing, all right? And the interesting thing is, the person who wrote the code for it, and this is where I tell my students, you better be a good computer scientist whether you're a theorist or an observational astronomer, because if you are not, you're not going to do well in astronomy, theory or observational. The person who wrote the code for this, his manual, he's French, and the manual he has is just like 2 web pages. And by 2 web pages, I mean literally 2 pages is all. And it's all these scripts and stuff you're running and all these programs. And the thing is, we basically, by trial and error, went through and figured it out. We still haven't figured it out completely, all the bells and whistles on it, but colleagues at Valpo and Ball State are using it now also and have used it for their research. And then I have other people calling us now, because my students have helped me figure out how to use this. I mean, I said, here. They said, well, how do I know what to do if there's a manual? They said, this is the way all astrophysicists work. Usually we don't read the manual, you know, with software. You try it out first, okay? And I said, actually, the best way to figure things out is trial and error, because you learn your mistakes that way, too. But anyway, so this shows one of the data files here. And this shows some of the, just from one cluster, some of the things we have. And notice, for instance, just to give you a little science here, this one's beating almost like a drum. If you hit a drum in the middle, it goes down and up, down and up, down and up. Well, if you hit it on the side, you can have these points where it has these ripples now in it. Instead of one big ripple, it can have 2 ripples. And these are the ones that are sort of oscillating in what we call the first and second overtone. And so they literally beat like drums. That tells us a lot about their densities, their temperatures, their mass, their ages, and their compositions. So that's why we're interested in this. But these are what we call short period variables, roughly periods from maybe a few hours to a day. To investigate long-term aspects of this, and to show you some of the long-term aspects, notice this variable right here. One time it's up here, then the next cycle it drops. And that cycle can be anywhere from 30 days to 2 years. Well, in order to study the secondary, what we call amplitude modulation, that means we have to study it for several years, close to 5 years or more, which means we have to hold on to all this data, all the analyzed data, for 5 years minimum to study these things. And then we got to continually, if we want to look at it, every season, pull it back up again and start working with it. So that's one of the issues we're dealing with. By the way, when we remote observe, we typically remote observe with a Mac or a PC, you can do either one, and then we download it to that specific laptop, desktop, whatever. Then we have to bring it down to our central server where we do the difference image analysis, because it has a lot more RAM for us to use and stuff. Then we have to bring it back to whatever iMac our students are using to process. So it's an issue of going back and forth, back and forth, back and forth. And then when we're in this phase and students are analyzing these light curves that I had shown you right here and the data, when they're doing that, and this is what I've uncovered just in the last 3 weeks, is my student he's constantly bringing his flash drive back and forth from our observational lab to my office. And I said, well, can you show it to me? Well, it's on the iMac. Okay, well, bring me all 500 files over here so I can look at it. So we get a flash drive out and walk it over to my office, because it's hard to, nearly impossible to go from iMac to iMac, okay, right now. This one thing, we need a central server, basically, where we can actually all access it and have high-speed access to that and access our data. So these are some of the points, what I call, and John will call the pain points that we're dealing with. Okay, so let me just move forward a bit here. One other curious thing about these clusters, there's a tiny little globular cluster, actually one we observed. Notice this dark streak here. That's a cloud of gas and dust. One nice thing about this is we can determine how much dust is between us and the cluster. In our work, we've suddenly gone from being theorists to being the premier group in discovering and finding these variable stars and globular clusters, which I never thought I'd be that kind of observer. Doesn't mean I'm doing it well, but I'm doing it, okay? And the fact is we have 80 nights a year. That means we can do this continuously, basically, throughout the year and study things. And as I said, remember, big telescopes like the Keck telescopes, things like that, you get 3 nights a year on them if you're lucky. That's not enough time to do all the work we do. And also that work would not, the Kecks would not work on projects like this because the stars would be too bright. You would have to take too short of images and it'd just be a waste of telescope time. But here, the fact that we have dust and it can vary, we can use our variable stars to determine the age of this cluster, the distance to it, things like that. And this tells us a lot about the history of the early universe. How did stars form? What were their compositions? How did our disk of the Milky Way form where we live today? So it really is going back in time and telling us the early star formation in our universe. Okay, and this just shows, I didn't mention this, but each point here is a single image equivalent. the star on that single image observed. And this is infrared, visual, which is green, and blue filter. So we produce a heck of a lot of data for each star. When I plot out these plots that look something like this, there can be, well, if you imagine 1,500 points on each plot, and then I might have, sometimes I put 30 variables on one chart here. Well, that's 30 times 1,500. The printer takes a while to get through all that. So I've noticed that as an issue too in just printing things out. So one of the other things that we have done, our donor, and we did this, he has a place up in Lake Wawasee, Indiana, and he invited me up there back in 2009 or 2010, and he said, well, come on up, Brian, I want you to see my house. He has this extremely green house. It has solar heating, it has everything on it, okay? And he is one of these, this guy has plenty of money, but what he does at night, if it's cool, he opens all his windows, has the air conditioning off, then the minute the sun comes up, he closes all the windows, okay? All of us running around the house, this two-story house. I was like, wow, okay, you are serious about this. But you really want him to see it. But while I was there, he said, well, let's go mud walking in the lake. And mud walking involves basically getting your swim trunks on and walking like this in water in the mud in the offshores about like this and just walking along. He goes, well, so-and-so lives there, so-and-so lives there. Okay, there's so-and-so, the disgraced CEO of so-and-so, okay, or whatever. And then he's going on, they said, and the provost had come too, and so we were talking, and she goes, well, what should I say? Well, here's what I want to sort of push him toward. I want him to say, you know, and by the way, he used to be a tour guide at our observatory. We get about 10,000 people a year to our observatory to look through our scope. And so he knew what I was dealing with. And I said, well, we really should take our 1954 telescope, upgrade it, and by that I mean change the optics a bit. Make it remote observing, just like the Sarah telescopes. And so we are almost done with that now. And because it's our observatory, that means we have a minimum, taking into account cloudy days and things like that, probably about 180 nights a year. There's another 180 times 2 gig times all the other multiplication of data analysis that we're going to have here on our own university, creating data. So, and just to let you some of the things we've gone now, we're going to large format CCDs, and the typical, basically the big thing with this telescope, we changed the optics. So it's gone from a very long focal length telescope to a short focal length telescope, which means our field of view has gone from this to 10 times larger now on our camera, which means we can do a heck of a lot more science with it, even here in the city of Indianapolis. Luckily, we are not in downtown Indianapolis. We're in a residential area. We have the White River and a lot of trees on one side of us. So we do have half our sky is relatively dark. And we have tested the system already. And by the way, that person there, Peter Mack, who Andrew here has met many times, a jack of all trades. Another PhD astrophysicist, but I'd say he's an electrical engineer, a mechanical engineer, a computer scientist, network. Well, you're a better networking person than he is, but anyway. But it's amazing the stuff I've learned just from working with this guy. And he's the only one who refurbishes old telescopes in the world. And he is totally overbooked. And so when he says, I can get it done in 2 years, you at least multiply by 2 with him on this thing. But anyway, so our telescope's going to be starting, probably coming into research use here in the next few weeks. And that means any clear night, we're going to be using it. And my colleague, Shenming Han, he goes to China every year. And the interesting thing about that, it's going to be daytime over there for him, so he doesn't have to stay up at night. He's going to be using our telescope from China and doing all his observations and just saving the data here at Butler. All right, why he's doing that. And that is one of the beautiful things about remote observing. That's why I like the Canary Island telescope. I can start observing at 3 in the afternoon and be in bed by midnight, because it's to the east of us quite a ways. So just to go review some of our issues that we have with this research, and we do find inventive ways around it. Flash drives are a big problem with, we have to use, but downloading data from remote observatories, transferring data from IMAX to process, moving processed images to the campus server for difference image analysis, moving resolving files on each star back and forth from IMAX, okay? And one of the things is sometimes when we download the data, we carry it just across the room, almost about like 20 feet across the room with our flash drives to put in the IMAX, because it's just easier to do that half the time than it is to, frankly, try to push it through the network, get it on a server, and do this and that. So it is one of the issues where having a central server where all this stuff can lie and having fast access to it to move the stuff back and forth, because we do have to move it back and forth, and that's probably our biggest issue. And then transferring, like I said, between faculty and students. And when students actually, like I said, they come to my office, I said, well, go get your flash drive. It's just easier right now to do that. So you see some of the issues we deal with. Astronomy is one of the most data-driven sciences there is. I was talking to, who is it, Sean, who's in our biology department. And I was reading this article. I said, well, Sean, I said, here, this telescope over here they're creating is going to have exabytes of data an hour. And the human genome is only 1 gigabyte. Okay, so, but it's interesting. It's just there's so much things. And because remember, in astronomy we just don't have X, Y, Z. We also have time. We also have luminosity. So we have multiple dimensions we're working at. We also have colors we're working with. So we're going in all these different parameter spaces and dimensions that we have to follow, which creates a lot of data for us. Yes, the initial image, it's not all that large, but what happens is once we get to the final product, we have produced a lot of stuff that we need to hold on to. So anyway, I'm going to hand it back to John, and he can comment on anything here, if you like. Do you want to go any further with it?
I guess I do have a question.
Sure.
When you talk about variance with the stars, does that include, this is going back to my how the universe works stuff here, we have a sun and planets revolving around the sun, dimming the light. Does that variance also include those types of things?
You're thinking of planetary transits, they're called, okay? Typically, the chance of having a planet in the plane, its orbit in the plane of that star as we're observing it is 1 in 10,000 of having it at any time pass through, okay? Most of the time, the planes of the orbits are tilted so they never pass in front of the stars. Now, that's what, if anyone's ever heard of the Kepler Space Telescope, which was launched specifically to look for Earth-like planets, it was looking for dimmings. As Earth-like planets would pass in front of their star, there'd be 1/100 of 1% dimming of that star. We're looking more on the 300% value down to maybe the 5% value dimming, so not down to the real small dimming, okay?
Okay. Yeah, if you don't mind, I'd like to talk a little bit about the
Here you go.
infrastructure side of this, wrap it up.
By the way, if anyone has questions, after he's done, I can answer any questions you have to.
Okay, so I'm just going to skim through a lot of this as quick as we can. We have 15 minutes. I'm going to try to add what's most relevant. I added Brian's process here, and we're going to flip through these pretty quick. Step 1 of Brian's process, observe something. Step 2, so step 1 is to identify something to observe. Step 2 is observe, and of course my telescopes aren't as good as Brian's.
That looks like my first telescope.
Oh. So what happens is after they observe, they move the data from the telescope to a PC in the observatory. From there, they move it from the PC to IMAX with students using thumb drives. Now, look at those thumb drives. That's a lot of work. But you see why that's kind of a problem, right? I mean, imagine the time that goes into making sure the right student has the right thumb drive. I mean, I just picture this stuff getting confusing and wasting a lot of time. And in any given semester, when you're trying to teach students, you really have to be on point, and you don't have time to be confused in any way. And this is just one piece that I think is agitating to Brian. So then they process the data and images on the IMAX. They transfer the data from the IMAX over the network to a server we have, and I believe that's where your ISIS application is. They do some preliminary analysis on the server. They compare the differences, which Brian showed us. Then they transfer the data back to the IMAX over the network for final analysis. And from there, they move it to Google Docs, which is where they do a lot of their collaboration. So there's a lot of emphasis on moving data around in the network here. After that, the papers are written and submitted to a research group. So as Brian mentioned, part of the problems we have are lack of central storage, is probably the most important thing. So we're sort of grateful that one of the grant opportunities emphasized storage for research. And since that just came out a couple weeks ago, we're kind of repivoting and rethinking of how to do this, even though we've been working on this for a year. Now, some of the fiber infrastructure limitations can be pretty significant. You know, we have Brian's research, but we also have Sean, who works in genomics and in biology. We call him Dirt Guy. You know, along with other researchers. And Butler, just a little while back, they got approval to build a new science building. With that, we're hoping to sort of consolidate a lot of our research people in there in our systems, and hopefully increase our research footprint as a whole at Butler. But to do that, our fiber infrastructure needs to be upgraded. So surely you guys are already noticing multiple things we kind of have to work on. We just have to pick the best one that satisfies the requirements of this grant. Some of our buildings are only connected through 1 gig links, and we have to ether channel those links. Our secondary internet is only 100 meg burstable to 500, which is a serious problem. Just imagine a situation where, now it's already, these guys already have to worry about cloudy days and other things that could prevent them from getting a good observance. So imagine some of their collaborators in China or what have you are connecting to our telescope, and you know that same day maybe we didn't have time to coordinate with Brian or all the other people. You know, maybe we have a vulnerability or a very DDoS attack happening on our primary internet circuit. Maybe we need to upgrade the adjacent directly connected switch for whatever reason. There are many reasons that our primary internet circuit could go down. And when all that traffic transfers over to our secondary circuit, that's going to be a problem. You know, people, you know, imagine if you miss the observance of Halley's Comet or something like that. I mean, that doesn't come every day. So we need to emphasize and look forward to strengthening our infrastructure as a whole, not only for Brian, but to lay the foundation to increase our research footprint as a whole. So some of the process we did when we heard about this, you know, we really didn't know where to start. And thankfully, we had organizational restructuring before I started at Butler, about a year, 2 years before I started. They developed a partnership team which bridges between IT and all the other departments. Thankfully, we were able to engage some of our account managers to go out and talk to the faculty and kind of get a broad spectrum of who we think could potentially be doing significant research. So that resulted in having Brian and several others, you know, Dirt Guy, a couple other people. We all got into a room. We invited iLight and Internet 2, which, by the way, if you guys go through this process, definitely involve them. They're so unbelievably helpful with this. We all sat in a room that started to get way too hot. We had each person discuss their pain points, and we took notes. And we were able to shave off 80% of them right out the bat. You know, they weren't science, and they weren't certain things that we needed. And at the same time, we got value because we wrote down their needs, and we now know that we can come back to those later. So in that process, once we knew what we wanted, we were able to develop a grant team, if you will. You know, it included IT people, it included our researchers, it included the grant office. We got a new director of grant something or other. We knew we wanted to capitalize on her new motivation, you know, being a new employee. Got to get her now before that dies down. So we got iLight and Internet 2 in there, and it's been a great team. So in summary, you know, we talked about Brian and his research, you know, along with other researchers doing stuff on campus, and things that they want to do, but they just can't do. And, you know, Brian, I think some of the things we didn't talk about to save, because we wanted to save time, is, you know, Brian and I have talked a little bit about potential e-learning with astronomy and kind of engaging community for these things. And, you know, if we can't get enough collaboration and people able to log into these servers, or you know, maybe even just streaming astronomical events, how do we really reach out to the community and get people interested in science, especially astronomy? So we talked about some of the pain points, submission process. That's it. Does anybody have any questions for Brian or myself?
I got one. So, like, did you guys actually get funded then from NSF?
Yeah, this is Mike with ID Solutions. Did you guys actually get funded then with the NSF, or is that still in process, ongoing? Like, is the final version kind of polished, or are you still trying to add things and whatever?
We haven't been funded yet. We, in anticipation for this, we kind of thought that the 2016 updates to the grant would come around January, I believe. So we had prepped all the way up to that point so that once it was released, we could hit the ground running. You know, at that point, our idea was that we would already have everybody engaged. Everybody's aware of who needs to do what when the time comes. Because we have other jobs, right? You know, we don't want to stay up until 3 o'clock in the morning making sure we're getting a letter of recommendation from a campus leader or what have you. And we just needed to make sure that we had something solid to work with. So now that we have all that, you know, of course, the new information came out a couple weeks ago, and, you know, some things have changed, but most of them are the same. So 80% of the work we've done is still very relevant. You know, now we just need to reassess, tie things together, and really think about how we're going to submit this. We're thinking about doing a couple. You know, Brian has talked about, you know, maybe engaging other universities involved in this research to set up sort of a shared collaboration and storage, maybe through some type of MPLS circuitry or something like that. And those are the bigger grants, but you know, we still need to reach out to those people to see if they're interested. You know, not only the faculty, but the IT staff of those other universities, to see if they could support it. So at this point, we're kind of taking a multi-pronged approach, and then we're gonna eliminate what just doesn't make sense and move from there. Anyone else? Come on, guys, shoot for the stars.
Don't shoot me.
I had to get one pun in there. All right.
Here's one.
Okay.
Certainly.
Actually, the one I was thinking about was a question you got asked about transit.
Yeah.
So when you were looking at that globular cluster, I thought, well, how many times or how likely is it that there's a star behind the star that's contributing to the light that you see?
Right.
And if that is the case, how do you tell the difference?
Well, what we do, we call them blends, where, you know, since the atmosphere is blurring the stars, if we get two stars close together, what we can do is we see its amplitude of variation isn't where we think it is, and also the color appears different than what that star should be for its amplitude and period. And so we just go to the Hubble Space Telescope image and look at that. And you might say, well, why don't you just use the Hubble Space Telescope to do this research? Because it's booked 24/7, 365, and they would not give us 80 nights a year for the project, okay? So we just use a single snapshot that they took to look at high resolution, what's sitting there where this star looks to be suspect. And referring to planetary transits, people have looked in the last 10 years, just stared at globular clusters to see if they can pick out these minute planetary transits. And they found a few Jupiters, but that's about it, okay? So part of the problem is there's just so many stars, and you have to look for really, really tiny variations in the star to find those. We're looking for somewhat larger than that.
Thank you.
So where do you fall on the Pluto issue?
Well, actually, after I teach my class and my students are saying, I have one person in a summer class I'm teaching, she says, Pluto's a planet. Now she goes, yeah, it belongs with its own kind, so to speak, okay? It's brethren in the Kuiper belt. Pluto has the advantage, and just to let you guys know, it's a sort of an interesting historical fact, it was the first object in what's known as the Kuiper belt discovered. When it was discovered, it was thought it was 20 times the mass of the Earth. It turns out now we know it's only 2,000th the mass of the Earth. So there's been a drop of 10,000 in what we thought the mass of Pluto was from its discovery to today. And we now know of 10,000 or more other objects that sit out there where Pluto is. So it's in this belt of objects. It's the brightest of them all, only because it's one of the closest. There's actually Eris, and that's the one that sort of knocked Pluto out of the planet club, because it's actually larger. So it's sort of like most people don't know in 1849 we had 22 planets. That's because as they're counting asteroids, they're including those in the planet list, and they realized, let's call them minor planets, okay? And so we went through the same phase in 2006.
Is there a common standard for the definition?
Yeah, the definition is it has to be round, which means it has enough gravity to pull it into a sphere. Number two, it has to orbit the sun. And it has to have enough gravity to clear out its neighborhood around it, which all the major planets have done, including the terrestrial planets like Mercury, Earth, Venus, and Mars.
In regards to the observatory in Chile, are you working with the government there to get more
Yeah, well,
bandwidth out,
we actually, it is, Cerro Tololo it's a joint operation between the US government and Chile. And there's numerous observatories all up and down the Chilean Andes. There are observatories all across that, from Europe, from China, from everywhere going up across there. And their main sites, Cerro Tololo is one of them, ESO, which is European Southern Observatory, another spectacular site. And they have the best food of any observatory I've been to, because it's a 12-nation Europe, and so they have to have all the cuisines there. The American is just typical American fare. But anyway, we are funded, I didn't mention this, but the observatories themselves, when you saw that Cerro Tololo Observatory, that was partially funded by our dues, our buy-in, I think part of Valpo's dues and Ball State, they came in shortly before us. That dues helped do it, but also the National Science Foundation gave us substantial money. Any one university, small university like us, wouldn't have got the money to refurbish one of those. But as a group, where you have all these students that it's going to help, so it's like 2 or 3 R1 universities put together as far as the astronomy goes. And the same thing for the Canary Island scope. And the NSF gave us money for that to go through the refurbishing. Also, they have given us high-end cameras worth about $100K each. Well, not given us, we had them built for us and a spectrograph. So we have great equipment on them, and we have totally refurbished optics on the telescopes. And that's why they are so good to use, and the fact that the software allows us to remote observe.
All right, well, thanks, guys.